And I think we'll go into the final section on probability. So welcome. Probability is quite a different topic really to a lot of the other topics, because we sort of have a lot of understanding about probability from our ordinary day-to-day life. We sort of get probability, we sort of think we know what the probabilities are, and we're comfortable with it. And sometimes we know that before we start getting equations, and the equations can put us off, and we sort of feel, I'm not sure which equation to use. Whereas very often if we go with our understanding, we might even be better off. At least don't put that understanding aside because you don't know what the equation is. So I'm going to go through some probability, I'm going to suggest some questions to you, and you're going to get the answers to those, I think, pretty well correct. And then we're going to put in the equations and hope that you still get them correct because you got them right in the first place. So it's just a thing about probability that sort of people sometimes stand back from it, and they needn't, because they sort of get it anyway. So let's start with probability. So we're going to start with the section on single outcomes. Remember now that this is a minor topic within probability. It's the start of a section, so we have this rectangular piece here. And if you just want to look at this section, then you can skip the others or whatever. So probability, single outcomes. So probability measures the likelihood of an event happening. So for example, something could be impossible or something could be certain on a scale. So impossible, unlikely, very unlikely, evens, likely, very likely, etc. So for the following events, decide how likely or unlikely they are to occur. The sun will shine sometime today. Well, I think in most places it did. So that's probably a good probability. If we said that about tomorrow, we mightn't be as certain, or about next, Thursday week. You'll win the lottery next year. You may, but it's probably unlikely. There will be 367 days next year, or this year. I don't think so. We may have felt that some of the days were long, particularly recently, but they're still not going to give us an extra one there. If you plug out the TV, it'll stop showing the program. I think that's reasonably certain. It'd be quite scary if it didn't, at least after a second or two if it didn't stop. And it'll rain sometime next year. I think we can say almost for certain, but you never know. So in all cases, the likelihood of an event happening is given by naught is less than or equal to p less than or equal to 1. So the probability could be as low as 0 or as high as 1. It'll never be more than 1. So if you get an answer more than 1, just made a calculator error. If you can't find it, that's fine, but maybe state that you weren't expecting it to be there because you sort of know it's wrong. So in addition to the likelihood in all cases, we might say the same. The sun will shine sometime today. I'd say possible. You'll win the lottery next year. It's probably most unlikely. So P is virtually 0. There will be 367 days this year. That's impossible. That's P equals 0. If you plug out the TV, it'll stop showing the program. Yeah, pretty certain that's a 1. And it'll rain sometime next year. Most likely P virtually 1. So in sample outcomes, when you're doing just one thing, when an operation is conducted, the results are called outcomes. So the possible outcomes when throwing a die is this word they use for a dice. Dice are generally 2 of them, but a die is just this 6-sided thing. And the numbers are 1 to 6. So they're the possible outcomes. If you have a bag with 27 red, blue, and green counters in it, the possible outcomes, if you only select one of the counters at random without looking in, is it'll either be red, blue, or green. And that's it. They're the possible outcomes. And the possible outcomes from selecting a card from a pack are spades, clubs, hearts, and diamonds. So if you're looking for a card suit, a pack of cards, there's 52 cards in it, and they come in 4 different suits, and they're the suits. So if you're looking for picking a suit, which one it is, and it's random, you have 4 choices. Now, when it comes to Formulae, this is the first. The probability that an event meets a particular condition is given by the number of ways it can meet the condition over the total number of ways possible. So, for example, if you were looking at what's the chance of getting an even number on the roll of a die, you'd say, well, how many ways meet the condition? maybe the numbers 2, 4, and 6 are even, and there's 6 possible numbers, so it's sort of 3 out of 6 possible ways. So the number of outcomes that meet the condition and the number of possible outcomes. The probability of not meeting the condition represents the probability of it not meeting the particular condition. And the probability of something meeting plus the probability of not meeting, and that dash should be there, should be 1. It's just hard to see. So P plus not P has to equal 1. Okay, something has to happen. So if they say, what's the chance of getting an even number? Well, if chance of an even number or not an even number, well, you get something. Okay. So let's look at the sample spaces here. These are questions that I'm going to ask you to do before you think about any formulae. And we're just going to do them nicely, quietly, not so much in our own head, but together, and we'll see if we get them right. And then much later we'll talk about the formula behind them that confirm what we were doing. So if you toss a coin, the sample space is you either get a head or you get a tail. Heads or tails, that's all it is. Only 2 sides to the coin, that's it. If you roll a die, you can get 1, 2, 3, 4, 5, or 6. They're the 6 options. And if you select a card from a pack of cards, this is the whole sample space. That's the curly bracket at the front and the curly bracket at the end to show it's a set. The ace of clubs, the 2 of clubs, the 3 of clubs, the ace of spades, the ace of diamonds, all the way down to the king of hearts. So all the various ways there. So where C represents clubs, S, spades, D, diamonds, etc., and ace represents ace, jack, queen, and king. So that's the whole sample space. So if you're asked to write it out, that's the sample space. So let's look at dice probabilities now, or die probabilities, or whatever, if there's just one. Roll a die and establish the probability of the following outcomes. What is the probability that you get a 1 on the roll of a die? So just think about the answer for that. You've rolled a die. What's the chance that you'll get the number 1? 6 options, all equally likely. How many conditions meet it? Just the 1. How many conditions are there? 6. So it's just 1 over 6, I would say. What's the chance of getting an even number on the roll of a die? How many even numbers are there? What's the chance of getting an odd number on the roll of a die? What would that be? How many odd numbers are there? 1, 3, and 5. What's the chance? What's the chance of getting an even number or a 1? Even number or a 1? How many ways of doing that are there? And lastly, an odd number or a 1. Is that the same as the one above, or is it different? Odd number or a 1, how many ways could you do that? Many odd numbers or a 1 are there? So the sample space for the roll of a die is given by 1, 2, 3, 4, 5, 6. So given that the sample space is 1, 2, 3, 4, what's the probability of the numbers meeting the condition and the number of outcomes? So let's take the first one. What is the probability of getting a 1 on the roll of a die? Well, there's only one number 1 there. There's 6 in total. One way of getting a 1, 6 ways in total, 1 over 6. That's the first answer. What's the probability of an even number on the roll of a die? Well, the even numbers are 2, 4, and 6, so there's 3 of them. Total number of numbers, 6. 1 over 2, 50-50, 3 over 6, that's the way. What's the probability of an odd number on the roll of a die? That should be 1, 3, and 5 there. 1, 3, and 5. I'll fix that. Over that, again, 3 ways of doing it, and you've got 1 over 2. An even number or a 1 on the roll of a die. 2, 4, 6, and 1. So 2, 4, 6 are the even, and the 1. They're all different, 4 different ways. So 4 over 6, so 2 over 3. This one here is strange. Odd number or a 1 on the roll of a die. Well, the odd numbers are 1, 3, and 5. And the 1 you've already counted. So the 1 doesn't add really much to you there. So it's still only 3 ways, over 6, so it's a half. Card probabilities. A card is drawn at random from a pack of 52 cards. Find the probability that the card drawn is either a queen or a club. How many queens are there and how many clubs are there? Well, let's look at the clubs first, and I've highlighted these in red, and there's 13 of those. How many queens are there? Well, that's one of them, the queen of clubs, then the queen of spades, diamonds, and hearts. But if you count them all up, you can't count that one twice. So if you count it in the clubs, you can't count it as a queen. If you count it in the queen, you can't count it in the clubs. So that's the set. So I've got 13, 14, 15, and 16. The sample space shows 13 clubs and 4 queens. However, the queen of clubs is in both sets, the set of clubs and the set of queens. So there's the actual clubs with the queen in it, and there's the queens with the queen of clubs in it as well. So we can calculate the probability using the formulae, number of outcomes. And we can see there that the queens are there, clubs are there, and this one's in the middle. So there's 3 queens that are not clubs, 12 clubs that are not queens. 3 plus 1 plus 12 is 16. So the total number of outcomes meeting the condition is 13 plus the extra 3. So 16 over 52. Or you can simplify that dividing by 2, so that's 8 over 26, or divide by 2 again, 4 over 13. And that's the end of the introduction to basic calculations of probability. So we now move on to a topic called mutual exclusivity. This is an important topic. It's saying, can 2 things happen at the same time, or does one rule out the other? So for example, if you roll a die, you can get a 2 or a 3, but you can't get the 2 of them at the same time. So it's either a 2 or a 3. But you get a 2 and an even number, and they wouldn't be mutually exclusive in terms of probabilities. So we've got to look at how the questions are phrased. So mutual exclusivity and mutually exclusive outcomes. Outcomes are said to be mutually exclusive if they cannot both happen at the same time. So when choosing a card from the pack, the card selected cannot be both clubs and spades. It's just got to be one or the other. It can't be both, or it could be neither, but it can't be both. An example of non-mutual exclusivity, when choosing a card from a pack, the card selected can be both a king and hearts. So hearts and kings are not mutually exclusive. There's an overlap there. So you judge this not by any formula, but just by the sense in the question, and say, could they happen at the same time, or are they things that couldn't happen at the same time together? Now, there's a special rule for mutual exclusivity if you want to calculate probabilities, and it applies only when things are mutually exclusive. So in cases of mutual exclusivity outcomes for a single event, their combined probability can be determined by adding their individual probabilities together. The special rule applies only in the case of mutually exclusive outcomes. And it's expressed as follows, that the probability of A or B is the probability of A plus the probability of B. So for example, if somebody said, what's the probability of getting a 2 or a 3 on the roll of a die? We'll just say the probability of a 2 plus the probability of a 3, because you couldn't get 2 and 3 at the same time. So you could add and use a special rule there. In set notation, you'd write that as A union or A antis B, equivalent of PA plus PB, or A union B is PA plus PB. So you just add the probabilities together. It's a special rule only if they're mutually exclusive. Now, where situations aren't mutually exclusive, or you don't know, for a single event, you cannot get it determined by simply adding their individual probabilities together. So the general rule now applies, and you can use this general rule every time, even when they are mutually exclusive. So the general rule, or the fuller rule, is that PA or B, the probability of A or B, is PA plus PB minus this thing here, minus the probability of A and B. Now, this is the probability of it being a 2 and a 3, and that can't happen in mutually exclusive, so that will be 0, and that's why we could have got rid of it. But in general, if it could be a king and a heart, you'd leave this bit in. So the general rule is that PA or B, the probability of A plus B, is the probability of A plus the probability of B minus this bit, the probability of both A and B happening. And in set notation, you say it's the probability of A union B is A plus B minus the intersection, intervere of A and B. So the general rule then is written as PA or B is PA plus PB minus PA and B. But this bit here is further defined as the probability of A by the probability of B given A. Now it's important. A and B, you start with A here and then B given A. The A must be at the end of that one. So it's the probability of A by the probability of B given A. And the probability of B given A means the probability of B given A. What's the probability that it's a 2 given that it's even? Or what's the probability that it's a 2 given that it's odd? Well, given that it's even, you have a chance of it being a 2. Like it could be a 2, a 4, or a 6. But if it's odd, there's no chance it could be a 2. So that's what we mean by the word given. Given that we know A is true, what's the chance of it being B? So the general rule can therefore be represented as follows. The PA or B is equal to PA plus PB minus this bit, PA by PB given A. And that's the general rule for all multiple events that you need. Okay, mutually exclusive or not. So here we say, roll a die and establish the probability of the following outcomes: an even number or a 1 on the roll of a die. Now, when we did this before, we said there were 3 even numbers plus the 1, so we got 4 over 6 or 2/3. P odd number or a 1 on the roll of a die, we said 3 odd numbers. We can't add the 1 in because we already have it, so that was only a half. So the sample space for the roll of the die is given by this. So P even number or a 1 on the roll of a die. The outcomes of even are 1 and mutually, of even and 1 are mutually exclusive. You can't be an even number and a 1. Doesn't happen. So given that, we can say that PA or B is even and then add the 1 in, because you can't be both even and a 1. So P even, or you'd say just the P even or a 1, the chance that it's even is 3 over 6. The chance that it's a 1 is 1 over 6. Add the two together, 4 over 6 or 2/3, which is what we got when we did it without knowing these equations. What's the chance that it's odd number or a 1? Well, the outcomes for the odd and 1 are not mutually exclusive, because you could be an odd number and 1. Now, you could be an odd number and not 1. You could be a 3 or a 5, but it could be. So the general rule is the one we've got to do, this one here, or even the fuller one here. P odd or 1, so is equal to P odd plus P1 minus P odd and 1. So what's the probability that it's an odd number? Well, that's 3 over 6, because there's 3 of them. The probability that it's a 1 is 1 over 6. But what about this odd and 1? P odd and 1 is P odd, starting with the odd at the other end, P1 given odd. So what's the probability that a number is odd? Could be 3 over 6. What's the probability that it's 1 given that it's odd? Well, given that it's an odd number, I'm down to 3 numbers, 1, 3, and 5. What's the chance that it's 1? It's 1 in 3. So let's see. The probability that it's 1 given that it's odd is 1 over 3. There are 3 numbers, 1, 3, and 5. There's 1 in 3 chance that it's the 1. So the P odd and 1 is the P odd by P1 given odd. So P odd and 1 is 3 over 6 by 1 over a third. So there's a 1 in 6 chance that it's both odd and a 1. I now go back to the beginning and I say, what's the chance if it's an odd or a 1? Well, it's the chance that it's odd plus the chance that it's a 1 minus this bit. So it's 3 over 6 plus 1 over 6 minus 1 over 6, and they cancel. So I'm left with just 3 over 6 or a half. So the being 1 didn't add to it. You already picked it up with the odd. So the probability of it being odd was 3 over 6. Putting in this or 1 bit didn't add anything really, because it was already included. So it stayed 3 over 6. Now, we got that answer ourselves when we thought about it before we knew all these equations, but now with the equations it still works, so we know it's there. Now, there's a small topic on the course called expected values, and that is where you have a game where all of the probabilities maybe have different outcomes or different payouts. So in this case, we're rolling a fair die. So if you get a 1, you get nothing back. If you get a 2, 3, or a 4, you get €8 back. And if you get a 5 or a 6, you get €15 back. So the question is, what would be a fair price to pay for that game to make that worthwhile? Now, obviously, there might be a margin in it for the person who's running the game, but what would be a fair price? So basically, if it's a 1, you get no money. If it's a 2, 3, or 4, you get €8. And if it's a 5 or 6, you get €15. Now we can look at this as probabilities as well. What's the chance of getting a 1? Well, you have a sixth of a chance of that. 2, 3, or 4, 3/6 of a chance of that. And here, 2/6 of a chance of that. So effectively, you've got 1/6 of a chance of no money. You also have a chance of 3/6 of a chance of €8. And you've got 2/6 of a chance of €15. And all of those chances are available. Now, only one thing will happen. When the die is rolled, you'll either get a €0, €8, or 15. But on average, you have a sixth of a chance of that, 3/6 of that, and 2/6 of that. So the way this works is it's quite a fancy looking equation, but it's not huge. That just means that the expected value of X, what's your expected value? And this is sigma, which is the sum of, almost like integral, but it says check for values of 1, 2, 3, 4, 5, and 6. So when X, so you say, I have a sixth of a chance of this happening, I have this chance of that happening, and this chance of that happening. So effectively what they say is, we do it in a table, and we say, if it's a 1, I get nothing, I have a 1/6 chance of that, and no money. 2, 3, or 4, €8, 50-50 chance. 50-50 chance of €8 is worth €4. 5 or 6, €15. 2 out of 6 chance, so a third of a chance of making 15, that's €5. So we add them all up together. So this X dot PX, or X times PX, is the probability of something happening by its value. So what's the chance? Well, you make no money, you have a sixth chance of that. €8, you have 3/6 chance of that, and 15, you have 2/6 chance of that. And the sigma says you add them all up together. Adding them all up together, you get nothing, €4 and €5, total of €9. And that's the expected value. So on average, people playing this game again, would probably make an average of €9. And that sort of makes sense in that we knew it had to be somewhere between 0 and 15. Couldn't be as low as 0 because there were some chance of making money. Couldn't be higher than 15 because that was the best you'd make. Most of the luck happened to be around the €8 bit for the three of them. So the fact that we get an answer of 9 isn't too bad because we've 2 chances of the 15 and only 1 chance of the nothing. So that's really where it worked out. It's almost like a center of gravity or a weighted average. That's what we have there in that. So now, that's that topic. We now look at a topic called independent events in probability, NAVSPLARK. So we're talking now about events that really, they don't depend on each other. The second event doesn't depend on the one that went before it. They're completely separate. So they talk about situations where if you go into a restaurant and you're choosing your main meal, it doesn't matter what you had for your starter. They're independent. Sometimes they talk about picking cards from a pack. If you pick a card from the pack and you get something and you put it back, then the second time you pick, that'll be an independent event because everything will be back to normal as it was. It won't be dependent on what you took out before. Now, if you take the card out and don't put the first one back, that's different. But let's look at independent events. There's lots of these, so there's part of your course on independent events. Independent events, in the case of 2 events or more, but let's take 2. If the outcome for the first event does not affect the outcome for the second, then the 2 are considered independent events. So a card is selected at random from a pack of cards and put back. before a second card is selected. The probability of finding a particular card on the second selection is not influenced by what the card was selected first. So if I pick out a card, look at it and say that's whatever, but I put it back, the next time I pick out a card, it's going to be the same. I have the same chance of getting whatever because they're all still there. Example of non-independent events. A card is selected at random from a deck of cards and not replaced. The probability of finding a particular card on the second selection will depend on what card was selected first. So let's say I'm saying, what's the chance of getting a king on the second card? Well, if I've taken out a king in the first set and haven't put it back, then there's only 3 kings left. So the chance will be only 3 kings out of 51 cards left. On the other hand, if I didn't pick a king out first and I knew that, there'd still be 4 left. So it'd be 4 out of 51. But it wouldn't be 4 out of 52 because 1 card will be missing. So let's look at independent events, and this is where you do put things back. A deck of cards contains 52 cards. A card is selected at random and put back before a second card is selected. What's the probability of getting a club followed by a king? Well, the probability of a club first is you look at the sample and you remember all the big lines of it, and you say there's 13 clubs out of 52, or 1 in 4. So there were 4 suits, clubs are one of the suits. So that's your probability. What's the probability that the second card is a king? Well, all the cards are back. So all the kings are back and all the cards are back. There's 4 kings out of 52, so it's 1 over 13. If I want to do both, I'd have to say this and this. So it's the probability of getting the club first and the king second. So it's this times this, that and that. So I multiply with the and there. So that times that is 1 over 52. And that's independent events. Now, we have a section now on sample spaces and tree diagrams. Now, all of these topics, if you're looking for them, then you'll see them on the various maths.griffith.ie. You can go back to them. And tá roinnt was Gaeilge Cumá gur féidir leat brenn uirthe go háirithe ar an cúrsa gan ála bhéal. So we look now at sample spaces and tree diagrams here, and we say, how do we describe what's happening? So when one operation has m possible outcomes and a second operation has n possible outcomes after it, the total possible outcomes is m times n. So the first operation must be performed before the second operation. So that sounds quite technical, but just imagine you might have, say, something like a meal in a restaurant, and you've got 4 choices for starters, 3 choices for your main meal. Well, then you have 4 for the first, 3 for the second, 4 by 3. You have 12 different possible ways of, working through that choice. So now we're talking about multiple independent events. It's not just one, it's independent events. Where there are 2 independent events, the probability of getting outcome A from the first event followed by outcome B from the second event is PA and B. It's PA times PB. So you multiply them. When you want and in there, and makes life more difficult, you must have chosen the first starter and the third main. This and this and this makes the overall probability smaller. So that and that, you're multiplying probabilities. Because probabilities are typically less than 1, the thing is getting smaller and smaller and smaller. Similarly, where there are 3 independent events, the probability of getting output A from the first one, B from the second, and C from the third is A and B and C probability, PA by PB by PC. So they could be quite small at the end. In cases where particular outcomes from more than one event are required, the probability of meeting all the conditions tends to be reduced by each additional condition. Remember that the highest probability of any individual outcome is always less than or equal to 1. So let's say if you've got just a half chance on each one, half by a half by a half is just an 1/8. So it really gets small quite quickly. So here's some examples. A 2-course lunch offers a choice of 3 starters and 4 main courses. Many different combinations are there in total. Using S1, 2, 3 to represent the different starters and to represent the different main courses, the following combinations are possible. You could have starter 1 and main 1, starter 1 and main 2, starter 1 and main 3, all the way down to starter 3 and main 4. So it doesn't matter which one you use for starter 1, you can have any one of the mains. If you use starter 2, you can still have any one of the mains, and starter 3, any one of the mains. So the total number of combinations is 3 times 4. A 2-course lunch offers 3 starters and 4 mains. What is the likelihood of a diner choosing starter 3 and main 4? So you look here and you say, that situation, starter 3, main 4, that's one way of doing it. There's no other starter 3, main 4. There's no other main 4 with starter 3. So it looks like we've got 4 times 3. So that's 12. And only one of them meets the condition. So the number of outcomes meeting the condition is 1. And the total number of outcomes is 12. So you could do it by writing out the sample space. Or you could say, what's the probability of starter 3, main 4? Is the probability of starter 3? Well, there's 3 choices there. And the probability of starter 4, main 4. So starter 3 is a third, because there's 3 of them. Mains, there's 4 of them. Third by a quarter, 1 over 12, the same answer. So there's 2 ways of getting that outcome, either through the sample space and watching it or spotting it, or through the calculations. Example 2, a tree diagram. This is where you grow it and you show all the options. If a restaurant offers a choice of 3 starters, 4 mains, and 4 desserts, how many different lunch selections can a diner choose? So you have 3 here, 4, and 4. So you can imagine here on starter 1, this is a tree diagram now. We say starter 1 could choose starter 1 and main 1, 2, 3, or 4. Starter 2 could do the same, choose any of the mains, as could starter 3. So together you can see that you have different choices for starter 1 and different choices for starter 2, and you see them all there. Now when you get to main 1, you can still have your choice on the desserts. So here's main 3, the choice of desserts. Main 1, and fill them all in, I think, and they're all there. So there's loads and loads of different paths through the whole thing. That's the full works there. So let's take one particular example. What is the chance that the diner chose starter 2 here, main 4 here, and dessert 1 here? Well, there's actually only one possible path. That's only one of the many paths that were there. It's not this one. It's not all the ones that come out here or here or here. So it's just one path. So there's only one way in which that can happen out of all the many that were there. The chance of them choosing this one or her choosing that one is 1 over 3, 1 over 4, and 1 over 4. So we can say there are 3 by 4 by 4, 48 different combinations. What is the chance of the diner choosing the particular one? Only 1 out of the whole 48. 1 out of 48 from the tree diagram. But you could do it this way as well. What's the probability of starter 2, main 4, dessert 1? So you separate them out. Probability of starter 2 is a third. Main 4 is a quarter, and it's and. You want this to happen, and that to happen, and that to happen. So not only do you need starter 2, but you also and want main 4 and want dessert 1. And that's why you have and that's why you have multiply in independent events. And that's why you get the 1 over 48. And that's that question. So that's independent events and the tree diagrams and all of that. The next are reasonably similar, but they're called conditional events because they don't always put the first card back, and things change because of that. So you might be picking fruit from a bag or something, or balls from a bag or something, and it says if you've taken a yellow one out and many are left if you don't put it back. But again, the logic can be understood from the question. So you just follow each event as it goes through. So a conditional event or a dependent event, in the case of 2 events, if the outcome for the first event affects the outcome for the second event, then the 2 are dependent. So one is conditional on the other. So example of conditional events, a card is selected at random from a deck and not replaced. The probability of finding a particular card in the second will depend on what the first card was. A bag, now an example here is a bag contains 3 apples and 3 oranges. A person selects a fruit from the bag without replacing it. The second person then selects another fruit from the bag. The probability of the second person selecting an apple will be influenced by the selection made by the first person. So you have 3 apples and 3 oranges. If the first person picks an apple, then the next person has only 2 apples left out of 5. So the probability would be 2 out of 5. If the first person picks an orange, then there's still 3 apples left. So it'd be 3 out of 5. So it depends really on what happened first. So a bag contains 3 apples and 3 oranges. 2 fruits are chosen without replacement. What is the chance of getting an apple followed by an orange? So we want an apple first. So what's the chance of getting an apple? Well, there's 3 apples in there out of 6. So it's 1/2. What's the probability that the second is an orange, knowing that the first is an apple? So this is where you've got to follow the question through. The first apple is gone. Now the probability of an orange is the number of outcomes meeting the condition over the total number of outcomes. We know that there are 3 oranges remaining out of a 5. So the second fruit is an orange. Well, we should have 3 out of 5 chance. What's the probability of an apple followed by an orange? We want the apple and the orange second. So apple first is 1/2 or 3 out of 6. Orange second is 3/5, and means 1 times the other, because we want this and that for the events. And then we say 1/2 by 3/5, 3/10. So there's a sequence of events. That's why we have the and there, but it's conditional. It's changed because we've already taken an apple. So that's that one. Now, I want to take a minute or two on combinations and permutations, because I believe this topic is easier and more understandable than it sometimes comes across. There are formulae for combinations and permutations, and you can get the answers reasonably quickly in probability. Probability isn't a question that you run out of time on, but it's a question that you say, did I make the right assumptions? So it's important just to think about what's really going on, because once you make the right assumptions, you pick up the answer very quickly and you write it down. So what do we do with combinations and permutations? Combinations is how many ways can things happen? Really, what's going on? What can happen in various events? Sorry, combinations are what things can happen. But permutations are, does the order in which they happen matter? Does it really care to me? So I'll talk about this in a minute, but just imagine the following situation where you've got 8 people in a race, and it might be the Olympic 100 meters final or breaststroke, whatever, 8 people in the final or whatever. There are 3 people that can get medals. So how many ways can 3 out of the 8 get medals? Well, you've got to ask yourself, is that a combinations question or a permutations question? Well, England, Ireland, and France get the medals. That's great. That's the 3. But does it matter who gets gold, silver, and bronze? Well, in something like the Olympics, I'd say it matters quite a lot. So the order in which they come in, that's really important. So in that question, if you were looking for the final in an Olympic final with 8 people, you'd say, you know, that's a permutations question. Now, if it was 8 people that you had as friends and you wanted to bring, maybe give 3 an invite to a particular show or something like that, or a concert, or tickets you got for something or whatever, then as long as the 3 get it, it doesn't really matter who gets it first or second or third. I mean, it's just tickets to the show or tickets to a concert or whatever your invitation is. So that's a combinations question, not a permutation question. So let's just look at the logic as you go through this and say, what's really going on? Because when we've got the logic done, the rest sort of falls away and it gets easy. Now, with the combinations and permutations, there's a number of formulae, and These are the ones that are in the tables. You can look them up. And you've got this symbol now called n factorial. It's like an exclamation mark. But the factorial of 5, for example, is 5 by 4 by 3 by 2 by 1. It's just a shorthand way of writing that. 3 factorial is 3 by 2 by 1. 2 factorial is 2 by 1, etc. N factorial is all the way down to 1. Naught factorial, by the way, is 1, as is 1 factorial. There's a formula here for, and we'll use these as our pages that we'll come back and work with. This is our toolbox that we'll hold on to. Combinations, the order is unimportant. It's just a selection of objects in any order. And the formula says that NCR, written like this, or NR this way, is n factorial over n minus r factorial or factorial. It's also written like that. You know, either n or is n minus r. So that's the way it works. So we'll keep that formula there. We'll come back and use it in a minute, but for the moment, we'll just say there is a formula. Permutation is much the same, but the order is important. So the arrangement of a number of objects in a definite order. And here we've got NPR. So it's NPR. It's n factorial over n minus r factorial. Now, it's like the other one. It's like NCR. But it doesn't have the extra bit on the bottom. It doesn't have the r factorial on the bottom. So there's always going to be at least as many permutations as combinations, okay? So let's look at the logic of this. Combinations. You have 4 close friends. I know you've got millions, but let's say you've got 4 friends that are close. You get 2 extra tickets to a concert and you'd like 2 of your friends to come. Now you don't have 4 tickets, you have to decide. It's a tough call. How many ways can you allocate the tickets? Now, I've given the friends A, B, C, D names, so apologies. Adam, Brian, Kira, and Donna. So they're the 4 names, right? So you've got to give them 2 tickets. So how can you do it? Well, you could give a ticket to Adam and Brian, or Adam and Kira, Adam and Donna, Brian and Kira, Brian and Donna, or Kira and Donna. In other words, out of the 4 people, you could say, okay, how many ways can I do this? Well, I don't know. I think I can give them, yeah, I can give it to, if I give it to 1, then I've only many different ways. So Adam, Brian, that's my tree. I've got Adam, Brian, Kira, and Donna. Okay? So I give out the tickets like that. Okay? And then this would be a Brian or a Kira, whatever. But let's see if they all work out as I've got all the trees, and let's see. That's the way I've got them, and I've sorted those out. Now, I've 4 friends, 2 tickets. It doesn't really matter who gets the ticket is the way I would solve that. Because as long as they get a ticket, they're happy. They're both equally welcome, you know? So you use the combination formula for 2 out of 4. So you say there's 4 friends, 2 tickets, it's 4C2. That's how you do it, 4C2. So 4C2 is, and you look at the Formulae equation for this, and you say 4C2 is, look at the formula in the equation for the C, and 4C2 is given by n factorial, n minus r factorial, r factorial. So 4 factorial over 4 minus 2 factorial, 2 factorial. Okay? So how do we solve that? So 4 factorial is 4 by 3 by 2 by 1. 2 factorial is 2 by 1. And 4 minus 2 is 2, so it's 2 factorial. So I get 24 over 4, which is 6. And 6 seems to be the number that I managed to get when I wrote the names out. Try to do this, but I wasn't sure that that was going to work, and I'll see. I'll write them out later and see Brian. So Adam, Brian, Adam, Kira, Adam, Donna, Brian, Kira, Brian, Donna, and Kira, Donna. Now, so that's combinations. Let's look at permutations now. You have two gifts that you want to give to friends. The first is a music voucher and the second is a travel voucher. So you've been given two presents. One was a music voucher for Spotify or whatever, some allowance or whatever, or something that you have. And the other is a travel voucher you got for, or it might be, somewhere nice. How many different ways can you allocate the gifts amongst your four friends? Now, assuming that each pair starts with the music voucher, followed by the travel voucher, Adam you could give the music voucher to, and then Brian the travel voucher. You could do Adam, Kira, Adam, Donna. Then you could do Brian, Kira, Brian, Donna, Kira, Donna. But look at this one here. Adam and Brian and Adam. In the first case, Adam would get the music and Brian would get the travel. But in the second, Brian would get the music and Adam would get the travel. And that's a different outcome. That's like the gold and the silver, the gold and the silver. So in this case, we're picking up 12 outcomes when we work them all through, not just 6. How would we have done that with the formulae? Well, we would have said we have 4 friends, and 2 gifts. But the gifts are different. So the outcomes differ depending on which gift a friend gets. It does matter. So here we say, really? What's the question? I have 4 friends, 2 gifts. The outcome matters, 4p2. Which one you get? It's 4p2. So 4p2 then is, again, we just look at the formula for p and we say, what's the formula for p? And it's here somewhere. And it's n factorial. NPR is n factorial over n minus r factorial. So it'd be 4 factorial over 4 minus 2 factorial. So if we look at it here, that's 4 by 3 by 2 by 1 over 2 by 1. So that's 24 over 12, or 2, which is 12. And 12 is the number of options we got. Not 6 anymore, but 12. So the question really is straightforward. Another way is to multiply 4 times 3, in that you say, well, how many choices do I have for the first one? I have 4 friends, so I have 4 ways of doing it. How many choices for the second one? 3 ways, that's 12. Because I have A, B, C, D here. And depending on how many I pick, I have 3 left. So that's the answer. Why did that not work the first time? Well, I had 4 friends and I could have picked 4th and then, but for every AB I had, I also had a BA. And when the combinations, and they were just the same thing, just inviting me somewhere, then really I was double counting. So that's why it was 12 over 2 for the combinations and 12 for the permutations. So that's how it works. So really you got to ask yourself is, how many people are there? How many different outcomes? Is it a P or a C? And then that's it. Okay. Now we look at these panels and these elections that can happen. A school student council needs to elect a female chairperson and a male chairperson. Ellen, Rachel, Beth, Sarah, Orla, Sheila, Brian, John, and Stephen and Matt are all candidates. I haven't worked out all those, but let's assume that 1, 2, 3, 4, 5, 6, there are 6 girls there, I think. Brian, John, Stephen, and Matt, and 4 boys. The students have elected Beth and Matt, so therefore you're down to 5 girls left and 3 boys left. They now must elect a deputy female chairperson and a deputy male chairperson. So they're down to 5 girls and 3 boys. What is the probability that Stephen and Ellen fulfill these posts? So it now looks as if we've got 5 girls and 3 boys. 5 girls, 3 boys. Okay. The probability that, now, if there's 5 girls there and Ellen is one of them, well, then there's one chance that the chance that it's Ellen as a girl will be 1 in 5 if you have to pick one of them. And the chance that it's Matt as a boy will be 1/3, because there's 3 boys and 5 girls. The 2 events are independent, so regardless of who you pick for the girl, you can pick anybody from the boy. So if you want this and this to happen, PE times PM, which is 1/5, by 1/3, which is 1/15. And that's how you get Ellen and Stephen in the group. 1/5 and 1/3 multiplied by each other. And that's how that's done. Now here's a nice question, a good exam question. And we're saying 5 girls and 4 boys are members of a social club, social group. I'll let that focus. They wish to appoint a committee of 4 people to organize a group trip. How many different ways can the committee be formed under the following circumstances? If there are no restrictions, if there has to be at least 3 girls on the committee, or if there has to be at least 1 boy and 1 girl on the committee. So this is a nice question. 5 girls and 4 boys are members of a social group. So let's imagine now that you've got girls 1, 2, 3, 4, 5. You've got 5 girls and you've got 4 boys. Boy 1, boy 2, boy 3, and boy 4. How many different ways can a committee be formed under the following circumstances? They wish to appoint a committee of 4 people. So they want to pick 4 people from all of these. They're picking a committee. They're not saying the president, the vice president, the treasurer. They're just committee members. So is the order important? Not really. As long as you get on the committee, you're on the committee. If you don't get on the committee, you're not on the committee. So how many ways can that happen? Well, how many people can we pick from? 9. How many people do we want on the committee? 4. Is the order important? No. As long as you're on the committee, you're on the committee. The answer is 9C4. And that's 9 factorial over 9 minus 4 factorial, 4 factorial. And that's the answer. So we look at that and we say there are no restrictions. 9 factorial over 9 minus 4 factorial. Write them all out, work it out. 126 ways in which that committee can be formed. Okay. Now, in the next question, it says there has to be at least 3 girls on the committee. Okay. So now you've got G1, G2, G3, G4, and G5. B1, B2, B3, and B4. There must be at least 3 girls on the committee. Okay? At least 3. Well, let's try to find out how many ways there could be exactly 3 and exactly 4. So how many ways could we get 3 girls on the committee? So let's just do the 3 girls on the committee, exactly 3. If I want 3 girls on the committee and there's 5 to choose from, I can say there are 5 girls, I want 3 on the committee, and the combination question, because the order doesn't matter. If there are 3 girls, I'll need 1 more person on it, and that's a boy. There are 4 boys to choose from, and I'll want 1 boy. And regardless of what I do here, I can multiply here by all of those as well. So that's really cool. Okay, so they're my combinations of that. So many ways can I do that? 5C3. So 5C3, so exactly 3 girls. I can say is 5C3. So that's 5 factorial over 5 minus 3 factorial, 3 factorial, which is 5 by 4 by 3 by 2 by 1 over 2 by 1 by 3 by 2 by 1. And for that, I get 10. So there are 10 ways in which I can choose 3 girls from that committee. This leaves the remaining place on the committee available for a boy, but there are 4 boys and I can pick one. So 4C1 is, well, it actually turns out to be 4, which is a long way of showing in a formula, but we're really saying that 4 boys, pick one. How many ways can you do it? 4. So the two together is that for each of the combinations of the 3 girls, we could have it with any of the 4 lads. So that's 40 ways. So there's 40 ways of getting exactly 3 girls on the committee. But this question says there has to be at least 3 girls on the committee. What about the situation where we might have, say, 4 girls on the committee? That would also do it. So now we've got girl 1, girl 2, girl 3, girl 4, and girl 5, B1, B2, B3, and B4. How many ways can I get 4 girls on the committee? Well, there are 5 girls in total out of. I want 4, and it's a combination question. So again, I do 5 factorial over 5 minus 4 factorial, 4 factorial. And that turns out to be 5. And that's not surprising. If I want 4 girls out of the 5, I can leave out girl 1, 2, 3, 4, or 5. 5 different ways. So there's 5 ways in which I can get, and if I've got 4 girls on the committee, there's no place for a boy anyway. So there's only one way of doing that. No boys get on the committee. So there's the 5. So that's another. So there's 40 ways of having 3 girls on it, 5 of having 4. That's 45 ways in total. So 45 ways of doing that. So that's the second question. That's getting if there's at least 3 girls on the committee. And the last question, if there has to be at least 1 boy and 1 girl on the committee. At least 1 boy and at least 1 girl on the committee. How would I do that? I want at least 1 boy and at least 1 girl on the committee. Well, I could try 1 boy, 2 boys, 3 boys, 4 boys, etc. Maybe a simpler way is to say, what's the probability of no boy on the committee? Many ways can I have no boys on the committee? Well, that would be all girls, so that would be 5C4. That would be no boys on the committee. No girls on the committee would be 4C4 for the boys. I'm picking out a 4 and I'm picking 4 of them. So there's only one way of doing that because all boys have to be on it. I can do the factorials, but it works out to be whatever. It works out to be whatever it is. That will work out to be 1. 5 factorial will work out to be 5 because how many ways can I get 4 girls on the committee? I have to just leave out either the 1st, 2nd, 3rd, 4th, or 5th. So there's 5 ways there. So there's only 6 ways really that I can actually work out that I break the rule. So there's only 6 ways out of all of them that wouldn't have a mixture of boys and girls. So the number of ways of having exactly 4 girls is 5. That's 5C4. Exactly 4 boys, it's only one way. All 4 boys have to be on it. So that would give a total of 6 ways in which you'd have all girls and all boys. So out of the 126 originally, you'd have 6 left. 120 are valid, would have some sort of gender balance. There'd be both boys and girls on it. And that's the end of that question. But you can see, hopefully it was handy to do with the just how many are there, how many do you want, is it a combination, work out the number, and that's your answer. So that's that. So we're coming now towards the end. We're on the binomial distribution. And this is a lovely topic, really. And there's a few observations in this as well. So we'll just take this one and see how this goes. The binomial distribution happens a lot where there's many events that can either be one of two things. So for example, you can have an event that's a win-lose, a dry or wet day, boy or girl maybe on the birth or something like that. So you can look at various options like that. So the binomial distribution is applied to situations involving repeated events. So you're having many of the same event where each individual outcome has only one of two possible values. So let's look at this question here and just ask yourself, do you think you could answer this question off the top of your head? In a very simple, not at the top of your head, but in very simple one line or two lines. If the probability of rain during any particular league football match is 0.2, 20% chance of rain at any match. Find the probability that a supporter who attends 7 matches in the season will watch exactly 3 in the rain. So what is the chance that somebody who goes to 7 matches will see 3 in the rain if generally the probability of rain is 20%? Could we write down the answer for that? It seems like quite a difficult answer, but let's see how we might do it with the binomial. The binomial distribution says there are things called Bernoulli trials. And Bernoulli trials are ones that either are yes or no, boy, girl, wet, not raining, etc. So these are the conditions they have to meet. There has to be a finite number of trials. So in this situation, the person is going to 7 matches. So that's okay. Only 2 outcomes on each occasion. It's either going to be raining or not raining on the given day. So that met. The trials are independent of each other. If it rained at the last match, it doesn't mean that it's necessarily going to rain at the next match. So they're not dependent, they're independent events. So that's important. And the last one is the outcome probability is the same each time. There's a 20% chance of rain every time. It doesn't get worse at different times of the year. So if we're assuming that this is the case, then we can use the binomial distribution. So that those conditions are met. This is the formula. NCR PR to the Q to the N minus R, or sometimes written as NCR P to the R Q to the N minus R. Looks quite fancy there. Q is really 1 minus P. So that's the probability of something happening. That's the probability of it not happening. So you could write it as NCR P to the R 1 minus P to the N minus R, because 1 minus P is the probability of it not raining. So if there's a 20% chance of rain, there's an 80% chance that it won't rain. So P is the probability of success. Let's say maybe call that rain this time. Q is the probability of failure, not raining. That's the number of trials, and R is the number of successful trials. So we want to know whether it's got 3 out of 7 wet days or whatever. So using the binomial formula in the sample question, we get the following. P is the probability of rain on a given match. That's 0.2. What's the probability of failure? No rain. That's 0.8. So that's the P and that's the Q. N is the number of trials. There were 7 matches the person went to. That's N is 7. And R is the number of successful trials. We wanted 3 to be in the rain. So what is the answer to this question? If the probability of rain is 0.2, find the probability that out of the 7, they'll have exactly 3. So let's see if we can find that equation wherever I put it, somewhere. I think it was here. So the equation said the answer is NCR P to the R Q to the N minus R. N is 7 matches. Or we want to be 3 with rain. P, the chance of rain is 0.2. Q, the chance of no rain is 0.8. So the chance of getting 3 rainy days out of 7 is as follows. N is 7, C, R is 3. P is 0.2. R is 3 because you want 3 of them. Q is 0.8. And if you got 3 matches that are wet, you want 4 that aren't, because N minus R is 4. So 3 wet, 4 not wet. And that's your answer. 7C3 is your factorial thing. So that's 7 factorial over 7 minus 3 factorial, 3 factorial. So that's 7 by 6 by 5 by 4 by 3 by 2 by 1 over 3 by 2 by 1 by 4 by 3 by 2 by 1. 4 by 3, 2 by 1 is that 3 there. So I think that says 21, maybe 105 or something like that. So 105, so the answer is 105 times 0.02 cubed by 0.08 to the 4. So we just write down the answer, really. There it is. There's the NCR bit. There's the other bits. We work it out, 11.48%. So it's pretty neat, really, to be able to take that question like that. It sounds quite complicated. And just almost with the one equation, just to, there it is, call out the answer. And that's the binomial distribution. Just an observation on the binomial distribution, you've got this thing called P plus Q to the naught is 1, P plus Q, P squared plus 2PQ plus Q squared. This is, if you might have seen this as Pascal's triangle at some stage along the way. It's quite a nice triangle. If you just multiplied the probability of P success plus failure, so 0.2 and 0.8 in the last question. If you do that once, twice, 3 times, 4 times, 5 times, you can see what would happen. So what to say here, if you went to 5 matches, this would be the match where you've got 1 wet day, 1 P, and 4 dry days, 4 Qs. But there's 5 different ways in which that could happen. There's 5 different ways in which you can have 1 wet day. Could be the first, second, third, fourth, or fifth match. So that's how you get that expansion. So 5 ways to get 1 success and 4 fails from 5 attempts. So you could succeed on the first, second, third, fourth, or fifth. And that's what that expansion is there. Briefly, if you were to imagine this as B plus G, or boys and girls in a way on a given birth, you could say, let B and G represent the probabilities of being a boy or a girl on a given birth. The term 3BG squared here would be that in a family of 3 children, there's 3 ways of having a boy and 2 girls. You could have the boy first, second, or third. So you could have boy, girl, 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 boy, girl, and girl, girl, boy. So they're the 3 different options. So there's 3 ways in which you can do that. There's only one way of getting 3 girls. There's only one way of getting 3 boys. And there's 3 ways of getting a girl and 2 boys. The girl could be first, second, or third. So if we look at those expansions, the highlighted row here, this one here, says that out of 3 possible, in 3 children families, or, you know, 3 children, and, you know, we look at this and we say, well, how many different ways are there? There are 8 possible arrangements. You could have 3 boys, boy, 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 2 boys and 1 girl, 3 arrangements, because it could be boy, girl, girl, etc., all the combinations. 1 boy and 2, again, 3 arrangements. The boy could be first, second, or third. And 3 girls, only 1 arrangement. So you have a 1/8 chance here, a 3/8 chance here, 3/8 chance here, and a 1/8 chance here, all adding up to 1. Because remember that P plus Q, or 0.2 plus 0.8 for the weather, or 0.5 plus 0.5 maybe for the boys and the girls, they add to 1. So each time you multiply it and square it, still stays to 1. So all the probabilities have to add up to 1. So I just thought I'd state that. And now this brings us to the very end of the section on the normal distribution. This is a lovely topic. And really what it is, it's about using tables. Tables that you're given, where you look up numbers and you say, Does that make sense? And you should be able to do it and know it from the way the graph looks. You should be able to say, that's roughly what I expected the answer to be. So let's look at the normal distribution first. The normal distribution is this wonderfully symmetrical graph that actually explains how that's beginning to get a bit of a shake, I think. We'll see. Hopefully it's okay. We might just do it with it seems to be pulsating there a little bit. So maybe I'll just try it with without the dashed lines. Sorry about that. You'll see it in your notes the same way anyway, but I'll just trace under this if I can. And that's the normal distribution, and I'll put the ruler in there and square that as well. Okay. It's just that shaking with the actual camera is there. It just doesn't like the dashed line. So apologies for that. Okay. But you can see it there, and I'll take it as a. So what we have here is we have a thing called a sigma, which is a standard deviation. And what they're saying is that if we look at this graph, 50% of it is to the left and 50% is to the right. And within this space here, there's an additional 34%, 34 point roughly 13%. So if I started here, I'd have 50% in all this section here, and this would bring me up to 84% if I added the 2 bits. If I went again to about here, I'd pretty well have all of it. There's only about 2.5% here, 2.2% or something in that amount. So the vast majority is here. Okay, so that's how these tables work. So there's our graph, and it has a mean in the middle, and we tried then to look at the various ranges as we go through it. In this case, the mean is 0 and the standard deviation. So let's just look at that. Okay, and in the notes we'll say the standard deviation here is 4. We'll say that it's 4 rather than 1. So that should be a 4. Okay, now the question: the heights of female nurses has a normal distribution with a mean of 165.4 and a standard deviation of 4 centimeters. So what we're saying here is that nurses have a normal distribution of 165.4. That's their average height. Half of them are smaller, half of them are taller. With a standard deviation of 4 centimeters. So if I go up 4 centimeters, that's 169.4 would bring me there. So 50% are less than this. Another 34% are less than this one. So 84% are less than 169.4. Find the percentage of female nurses who are smaller than 160 and find the tallest 10%. So what we do is we look at the 160 and we say, well, if we go down here to 161.4, that'll be again 1 standard deviation away. And given that that's 34.13%, this would be 34.13%. And if we're looking for people who are smaller than 160, we have to go even below this again. So we go down to about here, and we say, well, if 50 is here, 34 is here, that's 84, that's a bit more. Probably looking at about 10% maybe, roughly. But the tables will tell us exactly, but we expect it to be around 10% maybe. And the other question then is, how tall are the tallest 10%? So if we were to look at all of this shape and say, well, that's 50%, that's 15% here, maybe that's about 10% left here. Let's say that's the top 10%. What is that height there when that's 10%? So that's really what we want to do. So the first question is, how far is 160 from the mean in terms of standard deviations? So we know that the standard deviation is 4. That length there is 4. We know that the mean is 165.4. And how far away is 160? So So let's see, 160 from 165.4 divided by 4 is 1.35 standard deviations. So I'm not interested in the numbers, but I'm interested in how many of these, how many standard deviations do we need? So we're definitely down 1, we're definitely down 1.35. So I want to go 1.35 from the mean. So that's what I want to look at. How do I find out 1.35 from the mean? So I'm going to look at the tables now and see how I might solve that. I'm looking at 1.35 from the mean. Now in this question, I was looking for how many people were smaller than this. But when I look at the tables, this graph here tells me this bit. It's designed to tell me the bit at the top. Now, because it's symmetrical, we can do this. But that's one standard deviation. That's a bit more. So I'm going to go down here, and these are measures of standard deviations. So 1, down to the next page, 1.3, and across to 5. And that's saying 0.9115. So what that's saying is that by the time I've got to 1.35 here, I've picked up 91.15% in the green area, in the shaded area. That means I've only got a little bit less left to go to make the 100%. So to get to 100%, it'll be 8.85%. So this 8.85%, given that, that 91% relates to the shaded area. So when I went down to 1.3 and across to 5, 91.5% of it was in this area, leaving 8.5 left. So my answer there was about 8.85. So if there are 8.85% of nurses who are taller than 1.35 from this side, then there must be the same who are smaller on the other side than 1.35 from the mean. So effectively we've answered that, and we found that 8.85% are less than 160. Now, the other question is, how tall are the tallest 10%? Well, this is taking the tables slightly differently. And here we say, okay, I want to use the same tables, but I want only to be missing 10% at the top. Now, to miss 10% at the top, I really have to have 90% in the shaded area. So I don't look at the number of standard deviations because I don't know how far out, but I want the answer to be 90. So I start looking around through this table, looking for a 0.9. And I can see here that I'm nearly at 9, just over 9 here. But this one here, 0.8997, that's really close to 9. And that's at 1.28 standard deviations. So what that's saying is at 1.28 standard deviations from this mean here, that's 1 standard deviation there. That's 1 on the other side. That's just the sigma equals 4. That's one of them, 1 sigma. So if I go out there and say, okay, if I go to a bit more than that, if I go to, I think the number was the number, I think it was 1.28 of them. So 1.28 times the standard deviation, or 1.28 times 4 is whatever that is, plus the original number, I get 170.52. So 170.52 in terms of height would separate the tallest 10%. And that's the end of that question. So you can try these again and again, and you just start looking up the tables and seeing, am I using it to see the number of standard deviations, or am I using it to see the numbers in the middle?